Take an icosahedron. Pick 4 faces separated equally from each other and attach an octahedron to each. Cap each octahedron with another icosahedron. Now repeat the process, adding octahedra and icosahedra until the structure expands to infinity. This is I4T37, discovered by the crystallographer A.F. Wells in the 1970s. Because Wells built it using only platonic solids in a symmetrical fashion, it meets every one of our criteria for infinite Archimedean polyhedra. It's one of the most open infinite Archimedeans, with broad hexagonal gaps. But this object has an extra property. Every face is the same shape, in this case a triangle. It is monohedral. This episode is an exploration of the monohedral infinite Archimedean polyhedra, many of which were discovered or documented by Wells. If we instead attach 8 octahedra to each icosahedron, we get a different object. This is I8T39. The I tells us it is built from icosahedra, and the 8T refers to the 8 tunnels emerging from each one. The 39 denotes our 3-sided faces meeting 9 to a vertex. Note that monohedral does not necessarily mean face transitive. In this case, while every face is triangular, there are 2 distinct types of triangle, those occupying positions on the icosahedra and those forming the octahedra. We can also change our starting seed. Instead of an icosahedron, imagine a simple tetrahedron. If we attach octahedra to all 4 of its faces, the original tetrahedron effectively disappears. In this configuration, every single face in the entire infinite lattice is identical. This elevates the structure to a special status. It is an infinite noble polyhedron. If we use an octahedron as our seed, but build on only 4 of its faces, we get another infinite Archimedean. This is another fairly open structure, with large hexagonal corridors encircled by intricate rings of triangles. Alternatively, we can build upon all 8 faces of our seed octahedron. Like the tetrahedral example, the original seed is entirely hidden within its own expansion, making this another infinite noble polyhedron. However, the result here is far denser. This structure has an astonishing 12 faces at each vertex. It's so packed with triangles that it's difficult to visually comprehend the geometry. The tunnels are narrow, barely visible. We are probably looking at the upper limit of complexity. It seems unlikely that any infinite Archimedean exists with more faces meeting at each vertex. The last Wells object with triangular faces is built by attaching 6 octahedra to an octahedral seed. This is perhaps one of the more unexpected discoveries, with a somewhat flat appearance as the crystal grows out to infinity. The only other triangular monohedron I am aware of was mentioned in the previous episode. This is the repeated snub cube, built from a stack of snub cubes which has 8 triangles at each vertex. Moving from triangles to squares, we find ourselves on more familiar ground, at least initially. We have already explored the regular Mucube in an earlier video, along with the 2 infinite families of twisted and squashed Mucubes in episode 1. These 3 are all monohedra, but the list doesn't end there. Wells identified 2 further infinite polyhedra constructed entirely from squares. This remarkable structure, with 5 squares per vertex, features flying saucer-shaped discs intersecting edge to edge. The last monohedron with squares is a structure with 6 squares per vertex, the same vertex configuration as the Mucube, and a not dissimilar appearance from some angles. When it comes to pentagons, geometry becomes significantly more stubborn. Pentagonal faces rarely fit well with 3-dimensional symmetry, but this famous figure comes close. Discovered by J. Richard Gott in 1967, It's surprising this structure exists at all. It does very obviously have a lot of flat edges that violate our strict rules for an infinite Archimedean, but it remains a fascinating near miss. When we turn to hexagons, the list becomes remarkably exclusive. In fact, the only structures composed entirely of hexagonal faces seem to be the Muoctahedron and the Mutetrahedron, covered in the Petrie-Coxeter video. And that is as far as it goes. I don't know of any monohedral infinite Archimedeans with larger faces, such as octagons. Whether they are mathematically impossible or simply waiting for a future crystallographer to uncover them remains to be seen. Thanks for watching, and see you in the next video.